So, but there's a very big, detail still missing here, which is what? We're actually not done yet, right? Because, remember, let me erase this stuff. What I have here was a bunch of inequality constraints, right? But what we just saw how to solve was problems with equality constraints. Aha. So we still got something to deal with here. So now let's deal with that, right? And now I'm going to gloss things over a little bit more. The method of Lagrange multipliers is very old. It's, 200 or 300 years old. Surprisingly, the extension of that to inequality constraints was only done in the 20th century by these people called Karush, Kuhn, and Tucker. So let's see how that works, right? And actually, in terms of the basic intuitions, we actually can still pretty well understand what's going on. So here's how things work, right? Our new problem, right? So this is part 2 of our, the constraint optimization intro, is I still want to minimize my f of w, right? But now I have 2 types of constraints. I have equality constraints, as before, my h's, but now I also have inequality constraints, which I'm going to call g's, right? So g1, 2, 3, 4 are going to be inequalities, right? And in fact, in our problem, we don't even have equality constraints. So, let's just look at the general case, okay? So, I am still going to have my good old Lagrange multipliers for the inequality, my good old Lagrange multipliers for the equalities. Those are going to be my betas, right? But now I also need Lagrange multipliers for the inequalities, and I'm going to call those my alphas, okay? So, here's what we want, right? And these are known as the KKT conditions. When you hear people talking about, how to solve the SVR problem, you hear KKT this and KKT that a lot. So, these conditions are the conditions that characterize my solution. Right? Just like I had, conditions that characterize my solution in the case of Lagrange, of just having, let me see here. Again, let me erase this, right? My condition, right, was that the gradient of this function had to be equal to 0, right? This is what defined my solution, okay? That the gradient of the Lagrangian was going to be 0, right? And now the question is, what does the job of that, right? And then what we found was a set of weights that satisfy those conditions, right? So now what are those conditions, right? Well, they're a little more complicated. They're called the KKT conditions after Karush, Kuhn, and Tucker, right? The first one is still, it's the natural one. It just says that the gradient of my Lagrangian, which is now a function of 3 things, my original variables, and my Lagrange multipliers for the inequalities and the equalities, right? This has to be 0, right? So no big deal so far, right? This is fairly intuitive. All of these guys have to be non-negative as before. These guys all have to be less than 0, but this is really just repeating my definition of the problem, right? That the g's all have to be less than 0, right? I'm arbitrarily picking them to be less than 0 because it's more convenient. So nothing very surprising or very interesting so far. But here comes the really crucial part. It's this one. Actually, let me not even put a border around this one. Right? This is the key one. This is called the KKT complementary condition, or conditions, because it's usually a whole bunch of them. And notice what this is saying. It's actually going to make a lot of intuitive sense. This is something surprising, right? It's not something that, the others were kind of the obvious, but this one is not. It says that for each G, for each inequality constraint, the product of alpha of the corresponding multiplier times G is going to be 0, equal to 0. Why are they called complementarity conditions? Because these 2 things are complementary. The alpha and the G are complementary, meaning that one of them has to be 0. We know that at the solution, either the function is 0 or the multiplier is 0. Okay? Now, why is that the case? Right? Let's think about this graphically, right? So let me do a different illustration now. Let's suppose that I'm trying to solve my problem within this region, right? I'm trying to maximize, or let's say minimize my function as before, right? You get the idea. But now I have inequality constraints, right? As in linear programming, right? So now I want to find my optimum. This is a boring case because the optimum is actually in the middle there, but nevertheless, right? Subject to say, being higher than this lower than this, and higher than this, right? I have these four linear constraints that define a region, right, where I have to solve my problem. Okay? Everybody got this? Okay, now notice what's going to happen. This is the crucial thing. For each constraint, one of two things is going to happen. And actually, let me illustrate the two cases, if I can somehow draw this well enough, as follows, right? Let's say in one case this was the constraints, and in another case the constraints were, say, like this. Okay? Right, so same objective function, x1 squared plus x2 squared, right? The norm of the vector, right? Now one of two things is going to happen for each constraint. One is, and remember the constraints are these straight lines. One of the things that can happen is that constraint doesn't affect us, because I can satisfy the constraint while having my optimal solution. In particular, in this case, which I accidentally turns out to be very convenient, right? Even though I didn't draw it with that in mind, maybe in the future I will, right? All the constraints are inactive. This is really what the KKT complementary KT conditions are about. They're about which constraints are active and inactive. What does it mean that the constraints are active? Is that they don't affect the solution, right? Notice that in this case, right, my solution is exactly the same as it was when I had no constraints, right? Which means that I can get rid of the constraints, right? I don't need them, which means I can make their alphas equal to 0, right? Ignore them. Life is good. Now, of course, what's going to happen more often, right, is that some of the constraints are active, meaning that they are the constraints that we're bouncing against. And remember, we're in very high dimensions with a lot of constraints. The constraints that are active are the ones that, like, oh, there's my optimum over there. I want to get to that optimum, and then I bump into this wall, right? These are the constraints that are active. So, for example, in this figure here, right, this constraint is not active, right? Actually, let me do this. In blue are inactive constraints, right? And remember, each of these constraints is a whole line, right? These blue lines are not changing where my solution is going to be, right? So those are inactive. Their alphas, their multipliers are still going to be 0, right? But now, bummer, there's this one. This one is definitely active, right? Because what I wanted to do was, like, walk this way until I got to there. But that one's preventing me from getting there, right? So this constraint is active, right? Everybody see this? Now, mathematically, what characterizes a constraint being active, right? It's that I am on the line defined by the constraint, right? My constraint was that g had to be less than 0, but on this line, g is equal to 0, okay? You see what I'm suggesting here? So here's the following very interesting thing that happens. This whole complicated problem, we've got lots of inequalities. At the end of the day, it just becomes a good old problem with only equalities. Because for each inequality, either it goes away because it's not active, or it becomes an equality because I'm bumping against the constraint, meaning that the equation is satisfied, right? So, like, let's say that this was my G1, right? And my constraint was that, G1 of x1, x2 is less than 0, right? What happens here is that G1 is equal to 0, okay? So the bottom line here is that solving this problem with equalities and inequalities is just the same thing as solving a problem where actually, this problem that I have here has no equalities, right? It's the function and these 4 inequalities, right? And what I'm saying is that solving the problem with these 4 inequalities is the same thing as solving a problem where 3 of them are just completely ignored and 1 of them became an equality, right? So, one way to look at this is, I can solve this by figuring out which ones I can ignore, and then I treat the remaining ones as equalities, and then I'm back to my good old, Lagrange multiplier problem with only equality constraints. Okay? Everybody follow this? Okay, now, what does this mean for support vector machines? What are the walls that I bump against? What in the case of support vector machines is an active versus an inactive constraint? This is really what it all boils down to. Remember, my constraints, right, were that the margin of each example has to be at least 1, right? And I said that my dual variables were going to be the example weights. Okay? And remember, the example weights are these alphas, right? So what is my support vector machine going to be? Right? Some constraints are going to be inactive, and some constraints are going to be active, right? What are the active versus inactive constraints? Oh, I don't have that anymore. Give me just a second here. Let's look at this figure. So here's my, my dotted line is what used to be my red line, right? So this is my bad hyperplane, right? This is my good hyperplane, right? And the dotted lines are think of this, the distance between these two dotted lines as the thickness of the slab, right? So what are my active and inactive constraints? Anybody care to guess?
The three that are on your margin lines?
Exactly. The active constraints, right, are the margins of the examples that have the minimum margin. They're these guys. These are the guys that I'm bumping into as I try to swing my hyperplane. Right? I can't move anymore in this direction because that would violate the margin constraints for this positive example. Okay? So the support vectors are the ones whose margin constraints are active. They're the ones whose weights are non-zero. These guys over here, who cares? I could put them somewhere else as long as it's not inside the slab. I could, make them disappear. The solution isn't going to change. Right? So this whole idea of the dual problem and the dual variables is virtually very, meaningful in the case of support vector machines, right? The dual variables are just the weights of my examples, and the reason why I'm going to get a sparse solution is actually something that we had already seen when we talked about nearest neighbors, that most of the time, most of the examples are not going to, have any role in defining the frontier. Right? I could get rid of all of them and focus only on the ones that really make a difference. And those are the ones with active constraints. Those are the ones with non-zero weights. Okay? Questions? Those are the support vectors. And this is a support vector machine. Right? Notice that if for example, I got rid of this negative example, right? Then my max margin upper plane would basically fall down like this, right? It would swing. So it's these guys that are holding it in place. These are the ones that are supporting the hyperplane, and that's why they call support vectors. Questions? So, in your daily life, you're probably not going to have to worry a lot about constraint optimization, provided you're using an SVM package. But you do very much need to understand that this is what's going on. Right? This is what's happening. When you get a bunch of support vectors out, you know what those support vectors are. They're the ones that are basically, that have the least margin and that you can't move, or the hyperplane would change. Okay. Now, here's a question to test your deep understanding of machine learning. What is going to happen to the number of support vectors as the dimensionality of my space goes up? If you can't answer this question, don't worry, it's late in the day, and, this is not a trivial question. But if you can answer this question, kudos to you. You're really ready to get, 4.0 in this course. Right. Let me give you a hint. Remember when we talked about instance-based learning? And, by the way, the answer is not overfitting. Right? But remember that when we talked about instance-based learning, we saw this very big problem, which was what? The second biggest problem in machine learning after overfitting.
Curse of dimensionality?
The curse of dimensionality, exactly. So where does that come into here, right? So far, we seem to be doing all these things where we're not affected by the dimensionality, right? But we know that, that sounds a little suspicious, right? Because the curse of dimensionality always kills you in the end. So my question to you, right, slightly more concrete than before, is how is the curse of dimensionality going to hit us here? And what does that have to do with the number of support vectors?
The number goes up.
It goes up. Why does it go up?
There are more axes that you can rotate on when you're swaying.
Yeah, exactly. Right? the more dimensions you have, the more support vectors you need, right? And now you might think, well, does it just go up linearly with the number of vectors? Well, no, right? You need examples to define in hyperspace where this plane is going to be, right? So, unfortunately, what's going to happen is that in low dimensions, as long as the problem is, decently learnable problem, you can have a support vector machine with a small fraction of support vectors, let's say, 1%. But once the dimension starts to get to something respectable, like say 100 or 1,000, you will probably find that your number of support vectors has risen to 20%, 30%, maybe even 70 or 80%. At which point your support vector machine is not looking so clever, at least from the point of view of scalability, right? You didn't throw away that many instances. You have like this heavy thing to move now. And as usual, there's ways to combat that, but it's good to remember things that way. Here's another way to look at this. Remember all these examples that we saw, those strange things that happen in high dimensions? One of which is all the examples start to be near the frontier, right? Remember the hypercube, and in high dimensions all the examples are near the wall of the hypercube? Well, the same thing happens with the frontier, right? The support vectors, right, the minimum margin examples are the ones that are very near the frontier. And guess what? In high dimensions, they're all near the frontier. Bummer. Okay, so this big mass of stuff that you can get rid of in these like little 2-3D illustrations, in high dimensions, often that big mass isn't, has gone away because somehow in that high dimensional space, in one way or another, every example is not too far away from the frontier. And as we're going to see, this is also going to affect the kind of generalization guarantees that we can get.